Hi there. I'd like to continue to talk about this paper about distributed graph filtering. So it's a graph cell processing, and I guess just a quick review. The setup we have there is we have this so-called graph filter, which basically we have a graph and a graph here, and then graph of course I have a number of nodes. It can be connected, can be it can be connected, or maybe it should be connected. I mean it can have loop, or it can maybe it doesn't have a loop, or it's just a tree. It's okay as well. So let's say I have this graph, and then let's say I have n nodes there. Then the graph cell processing is an extension of the classic cell processing. So we have a signal and graph. So in the sense, the signal is simply a scalar value. So on each node of the graph, I have assigned a signal value. Maybe this is x1, x2, x3, x4, and so on. And then I can put these signal values as a vector. So I can put it as a vector here up to x8 here. So I can have a linear graph filter. Would be like I have this is like the original signal, then I multiply by a matrix, and I have like the new signal is here. So we can't mention about extension of Fourier transform, like classic cell processing to graph cell processing. So we elaborate the last time is you can think of Fourier transform is just mapping of signal to sinusoidal basis. And the sinusoidal basis, why we have sinusoidal basis is because those sinusoidal bases are actually eigenvectors of a shift operator. So if you think of a classic 1D DSP, or not DSP, any cell processing, and DSP as well, it can be DSP, but even if continuous, it will be same situation. So if I have a shift operation, and if I have the consider sinusoidal signal, shifting this sinusoidal signal is just equal to multiplying to some, the sinusoidal signal here, I would just say a e to the power something, use j, or I can use j or use I. So I guess last time I used I. This is just an imaginary number there. So if we use the engineering convention, we use j here. So uj, I mean, if I shifted that signal, let's say I have a sinusoidal signal is like uj omega t, something like that. So if I shifted that, shifted by delta, then I will just have this is ej e minus j omega delta times e minus jt here. So this is I have this shift operation here of this guy. It's just equal to wait a sec, missing omega here. Yeah, it's just equal to the original signal multiplied by a constant number here. So you can see this is actually it means that this is an eigenvector of this operation, or eigenfunction of this operation. And if we just matricize everything, so now we discretize that, so the signal is a vector here, and this shift operation can be think of a linear operator. Then again, we will have then in that case, basically we'll have a discrete Fourier transform and so on. Then the sinusoidal component, or sinusoidal a sinusoidal signal will be an eigenvector of this shift operation in the discrete domain. And then if the discrete domain, then is actually will be a special case of a path graph. Essentially, if I have a path graph, if I have a shift operation that, in the sense I have original signal here, x2, x3, x4, x5, x6, and I shift it next time. If after I shift this, so I have this become 0, like x1, x2, x3, x4, x5. Then this shift operation is essentially if I can represent as a matrix some S here multiplied by this signal x1 x here, so we say x1 up to x6 here. This thing here is essentially a is equal to something like that 1 1 1 1 1, and then this is a off diagonal term, like the diagonal is all zeros here, so it's all zeros here, and the rest are zeros as well. And this will be, if you try to just verify it yourself, like it apparently it's just the adjacency matrix of a directed graph like x1, x2, x3, x4, x5, x6, like this. So then in this sense, like people think of, okay, let's extend this to a general graph. So extend it in the sense that even I don't have a path graph, and even though I don't have a directed graph, I will still assume that the shift operation will be simply the adjacency matrix. So then in the sense my Fourier transform, then again I'm trying to project my signal into eigenvector of this shift operation. So then if I think of if I decompose to get the eigenvector of S here, so S will be equal to U lambda U transpose, something like, and then the Fourier the eigenvectors will be just U here, right? So if I try to project X into the eigenvector, will be X times U transpose here. So because this will be essentially U1 transpose, U2 transpose, these are all eigenvectors, and transpose, and this when this row vector, each of the row eigenvectors multiplied by this thing here, we just get the projection, and afterward this will be the Fourier transform. So what I get afterward will be equal to the Fourier transform. This essentially is a Fourier transform to get maybe I call it x hat here. It's like the Fourier transform of x, and then I can do an inverse transform by multiplying U to get back x again. So let me write it out better. So what I mean here is then I have x, I multiply by U transpose. This will be the Fourier transform of x here, and then times U again. This will be a full inverse Fourier transform that will get back my original x. And again, when I get this U will be decomposed from this shift matrix here. Okay, that's basically what we talked about last time. And now what we didn't mention last time is okay. We briefly mentioned at the beginning is this paper, of course, it's about distributed graph filter, and the distributed idea here is we want to emphasize that the implementation is distributed, so it's not implemented in a centralized manner. So therefore, I may have each of these signal, maybe I really have a real graph here, maybe a social network or something, and then maybe each node will be a user here, and they have their own signal. And then when I want to compute this filtering over their signal here, I don't want to compute in a centralized manner. I don't want to send my signal to maybe a centralized workstation and then compute the value and send it back. But instead, I want to propagate the values. Maybe I want to ideally I want to do a filtering that I only need to use my labels signal to compute my next filter values. So in the sense we call this kind of idealized filter a local filter. So in a sense give a more precise definition. I have a local filter. Actually, I didn't explain really very precisely. I can't like say local filter and distributed filter. Like they have very similar kind of conceptually very similar motivation, but local filter is more strict in the sense like when we talk about okay, let me give the definition it become clear. When I say local filter here, I'm saying that like my filter will only depends on, let's say H is a local filter. I guess I give a very precise mathematical definition, then it will become clear. H is a local filter if H Ij is non-zero only if I am J in the support of S plus I. So and S here, like S here is as I said, this is a shift operation with I guess I forgot what we remarked there. Like we assume here S is the adjacency matrix. This is adjacency matrix. So okay, maybe I don't even give a it's good to give a definition just as a review for the adjacency matrix. Adjacency matrix will be Aij is equal to 1 if and only if like Ij is an edge. So this is an adjacency matrix. Here I'm considering unweighted graph. So if I have weighted graph, this can be just a non-zero values. It can be like some kind of weights that will correspond to the weight of the edge there. So if I consider unweighted graph, I would simply say Aij is equal to 1 if and only if Ij is in E. So in this, let me use this as an example. Just make sure I pass the idea. I explain clearly. So if I use this example here, consider this as an unweighted graph. So my adjacency matrix will be well, this is pretty big. So maybe I erase a node or two here to make it simpler. So maybe just 7 nodes here, and then like I have from 1 to 7, right? So it will be a 7 by 7 matrix. So it have an edge from 1 to 2. So I have like 1 to 2. I have a 0 here. So maybe I have 3, 4, 5, 6, 7, and this is 1, 2, 3, 4, 5, 6, 7. I have like connection 1 to 2, and then the rest is all 0 basically, right? Well, at node 1 does not connect to anything else. Node 2 connect to 1, and then connect to 3 and 6. So I have 1 here and here, and node 3 connects to 2, and it connects to 4 as well. So I have like 1 here and here, and node 4 connect to 3. So node 4 connect to 3, I think it's here, right? And also like 5 and 7. Yeah, 5 and 7. And node 6 connect to 2 and 7. And node 7 connect to 4 and 6. Wait, I'm missing something, right? Oh, okay, look 7, 4, and 6. I think I missed out 6. No, 6 is 2 and wait. I think I did it. 1, 2, 3, 4, 5. Maybe I missed node 5. Is that? Oh, yeah, I missed node 5. I guess node 5 connect to node 4. Node 6 connect to 2 and 7. So node 5 connect to 4. Okay, I hope it's correct. So it looks a bit ugly. So this is the diagonal should be 0. So it should be a symmetric matrix. It looks like a symmetric. That's good. Okay, let's come back to the definition of local filter. So the local filter idea is very simple. So basically, it's just saying that okay, if I have I have the filter here for a node, let's say like x1 here. I will only like use my current signal like at x1 and also the signal at like my adjacent neighbor like x2 to compute my next value there. So therefore, as you can see, like this is beside the definition there. Like I will just have like non-zero, so therefore I should have only non-zero values for the filter when it's in the support of s plus I, because if we consider s plus I the support, okay, like the support here is like, okay, I've written here, the support is a very simple definition. It's like I have the support contain the index I and j if and only if like for the support of that matrix A here I have if and only if like Aij is non-zero. So if I have like so therefore like for example like for a diagonal matrix, then the support will be just the containing all the diagonal values like 1 1 and 1 2 like 7 7 here. So here I have support s plus I, so therefore like will allow to have like ij to include like the diagonal elements. And I mean for the what I mean is like the h can have diagonal elements to be non-zero, and also like only when only for the there's like an edge for the matrix there. Sorry, not only when there's an edge in the graph there will allow to have a non-zero value for hij. So is that clear? I guess I maybe give another example here. Like if I look at x6 here, what I mean is that I think this is pretty big. Maybe if I just make a small one, like x1, x2, x3, x4. I have this adjacency matrix because I have shift matrix is S here. So then I will have like S is here is just equal to 1 connect to 2, 2 connect to 3, 4, 1, right? And then like and 3 connect to 2. So it's something like that basically, I think. Let's see. And 4 connect to 2. I think I made a mistake here. Yeah. So it should be this here. Right. So this is the A matrix, or in my case it's also the S matrix here. So then the support of A plus or like S plus I here will be, I can have like, then I will have H. So I can have some H here. It can have non-zero values like here, 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 right? And also the diagonal. So I can have, for example, I can have a filter like this. So 3, 2, 1, 2, let's say 2, 2, 4, 4. Let's say I can have H, something like that. So this one will be local, because then you look at that like from this graph structure here, like it will only take values like from the labels, right? For example, like for the first element here, like when I have H, I multiply by x1, x2, x3, x4. Oh, let me just write it this way. So if I multiply by x1, x2, x3, x4, so I guess I write a stroke here. So if the next value here, x1, x2, x3, x4, maybe this is the filter value here. Maybe I keep a tilde here. So you see x1 tilde will be just depend on like x1 and x2, right? So it's 2x1 plus 2x2 here. And I have like x2 tilde, it depends on all values here, but they're all connected, so it's fine. And x3 tilde will be related, depends on like x2 and x4, right? So it also makes sense. So that's local filter. And of course, like, if we only restrict ourselves to local filter, it's very limited. So an immediate extension will be simply apply this local filter multiple times. So let's say I have a local filter H1, then I have local filter H2. So if I allow to have like some X here, I kind of like have a cascade of local filters, then immediately, for example, if I take this first example again, then if I just allow like one local filter H1 here, then my X6 will only depends on like, I mean the filter value of X6 here, the node 6 here, will depend on only the previous X2, X3, and X2, X6, and X7, right? But if I cascade two local filters here, then my future value of X6 will depend on like not just X2 and X7, but also X1, X3, X4. Because like first time, X2 will depend on X3 and X7 will depend on X4, and then we add pi again, then like X6 will depend on X4 and X3 as well. So that basically like this, we will call this a distributed filter. So it's a this, or like more precisely, I guess, a distributed implementation. So they call this distributed graph filtering here. Is, I guess, the filter itself is nothing to be distributed, because distributed graph filtering, I mean, if you just look at the matrix itself, you cannot say whether it's a distributed or not. But if you are able to implement in a way that like is either cascade of like this local filter, or like any other implementation depends on just the local filters, then we can claim that this is a distributed implementation. And essentially, like the paper here is just like it's one of the latest work like on this distributed graph filtering. It summarizes some of this earlier work and also compare with the work they propose. Okay, let's look at the earliest approach of like distributed graph filter. So let's consider any filter like, okay, there's any filter H here, and as I said, like we want to implement that H in a distributed manner. So it, as I mentioned earlier, one possibility is just decompose as a cascade of like local filters, but that may not be that easy. So the earliest suggestion is like, okay, let's just consider the shift matrix S here, and we're trying to decompose H as a polynomial of S. Namely, like I have H as a, for example, like A0 plus A1S, actually, so A0 plus the identity matrix plus A1S plus A2S squared, and so on and so forth. So maybe up to ANSN, and S to the power N. And S here, again, is a matrix, so let's say it's an n by n matrix, like maybe I have n node there, so therefore this maybe can be the adjacency matrix, or it can be like some other graph matrix, for example, like Laplacian matrix and so on. I think I made a mistake last time and say that like L is equal to A minus D, but should be D minus A. So D is just the diagonal matrix with the diagonal element is the degree of each node. Okay, and so this is like the first suggestion there, like earlier suggestion and earlier proposal, I would say, and apparently like this can be implemented in a distributed manner. S itself by definition is a local filter, so and I have like S to the power n can be implemented like distributively by just repeating applying S like n times. So then we just add all this together. So yeah, this is fine, but as you see, like this is actually has lots of quite a bit high limitation. And actually, before even talking about the limitation of this form here, maybe I would say like the connection of this with classic serial processing. More precisely, let's say classic DSP, digital serial processing. So where like if I have discrete time, if I have like discrete time and like I have the shift operator, maybe it's just the Z operator, So then in the sense like this is just a representation of filter in terms of basically the Z transform of the filter. For example, like if I have a filter can be written as A0, and of course typically I will have A1Z inverse instead, because I cannot have like a long causal filter, so it has to be a delay. So by convention, if we think of like the axis is time there, like we can only go forward in time, we cannot go backward in time, so therefore we can only look into the past but not look into the future and so on. So therefore, like, but in any sense, so this is essentially equivalent to a kind of the discrete Z transform, or basically simply the Z transform of a shift invariant filter. And this is shift invariant because I have the same filter applying to the signal no matter whether it's shifted or not. For example, I have a very simple signal. I just have a delta. It's just equal to some 1 here. It's essentially say I have like a time equal to 0. I have some kind of like I have a pulse there, and then there's nothing else in any other places. And maybe I have another pulse. Maybe I have 1 plus Z minus 1 and one time step later on, I have another pulse, I say. Now, filtering this thing will be just multiplying this filter by this signal here, right? So this is a shift invariant operation, because it doesn't matter like where I apply this filter. Maybe like I delay this operation like for like maybe 5 steps, let's say. Now I apply this after the delay of this filter. It is the same as like I'm applying this directly to this filter but delay afterward, right? So what I'm saying is that regardless what is that polynomial inside here, whether I consider I first delay my signal for some time and apply the filter, will be the same as I will just apply the filter immediately now and then delay the operation. Or you can think of like also like you essentially have a signal, like I have a peak here, I have the filter is applying here, and no matter my filter, maybe I write it like as a, okay, of course this is a bit kind of like sloppy here. So maybe I have a filter. This is I'm doing this with a convolution of this guy here. So I mean like this filter will not change over time. It's not like if my signal is here, it has a shape like this. If I apply signal here, then I have a totally completely different shape. So that's why it's shift invariant, right? And that's exactly the essence of shift invariant. Shift invariant is like your filter is not going to change its profile, like depending where it is, like when you're applying that. And an immediate consequence is that like also you see that like as captured in here, if I have a signal that is incoming, if I shift that signal for some time and then apply the filter, will be just the same as I apply the filter directly to that signal and then shift it. And also the immediate consequence is you can see that like the shift operation here with the filter itself actually commute. So more generally, like I may have like just shift 1 step, maybe just S here. If I shift 1 step, it's just an S operator. So I have like S multiplied with my filter is equal to filter multiplied by S. And this can generalize to graph filter as well. I can claim that like something is shift invariant if I have my filter, let's say my H filter here, some H filter here, if I apply S before I apply H, will be the same as I apply H then apply S. So if this two operations like commute, then I will have this, it will be like this. H is a shift invariant, then shift invariant with respect to this shift S here. And so let's see what else I should talk about. Okay, yeah, I just mentioned that what's the connection of this this form here with classic serial processing. So like it's very natural extension. Therefore, if you look at this here, and by the way, in classic serial processing, any shift invariant filter, apparently, first of all, like if I can write down the filter as a with its Z transform, then immediately you see that like I have this shift invariant property satisfied, right? So my shift here is just C here. So I apparently like it doesn't matter whether I'm of course by nature it should be, because whenever I write this, it just means that like I'm going to not change this, because then like all this coefficient is fixed, and it's not going to change values whenever I move to different places. But also like with the definition of this, also we see that like from the commutative definition of the shift invariant property, we also see that like the filter, well, as long as it can be represented as a polynomial of the shift operation, or like in the classic serial processing case, can be represented as a Z transform, then the filter is shift invariant. And also like it's actually this is like it's both a necessary and sufficient condition in classic serial processing. So if I have a filter is shift invariant, then I will be able to write it down like with this polynomial representation. So people kind of like thinking, okay, does it have the similar property here? So if I can write down the filter as a polynomial, by the way, like if I can write it down, say in the classic in the graph serial processing case, if I can write down the filter as a polynomial of the shift operator, then apparently I have like hs equal to sh, right? Because then I can just multiply s here, like maybe here, so I have hs, right? But then each of this sn here I can also write as s times sn, right? This thing apparently commute, then I will have like equal to a0 si plus a1s s plus a2s s squared, and so on and so forth. Then I can pull one of the s out, and then I will have like s a0i plus a1s, so on and so forth, an sn. So therefore I will have like sorry, like this is so hard to read. Let me erase some of this. Yeah, that's okay. So then and yeah, let me clean this out here a bit. So then I will have like I can erase this also here. Yeah, and maybe erase some of this here. So let's say this is h here. So then I will have like hs, of course, is equal to sh, right? This is like very easy to verify, as long as my h can be written as a polynomial of s. So what we have like one direction here is if like h is a polynomial of s, then hs equal to sh. But it turns out like in classical case, like this will be satisfied as well, but here it's not so simple. Actually, it won't be automatically satisfied. For one thing, it's like yeah, that probably like I would spend more time on it, but I won't like to extend talking about this. Maybe I will talk about more like in another video, like in more detail. I will need some conditions for this reverse condition to satisfy. It's not like as long as we have we have a hs is equal to sh, or like as long as h is shift invariant, then automatically I can write it as a polynomial of s. So maybe I will talk about that like sometimes in the future, but maybe not extend too much today. But it's just a remark here. It's not automatically satisfied. So at the surface, it looks like this filter has lots of flexibilities, right? Because I have this A0, A1, or I can pick arbitrary values. I mean, it looks like I can have this polynomial extend indefinitely, but it's not right. I mean, it's by basically up to a certain point, it doesn't matter if you add more coefficients here. It just doesn't give you another filter, because by so-called this Cayley-Hamilton Theorem, in linear algebra, basically if you have a matrix S, and if you consider the characteristic polynomial, that's basically I consider P lambda is defined as S minus lambda I, say the determinant of that. So this is a determinant, maybe I'll write it explicitly, determinant of that. So then this is a polynomial function, and the Cayley-Hamilton theorem is saying that you have Ps is equal to 0. So note that the difference here, this is a polynomial, like defined this way, polynomial of lambda. Now for this polynomial, I substitute S there, like S as a matrix, then I will get 0 there. So for example, my polynomial here maybe is 1 per 3 lambda plus lambda squared, let's say, plus lambda cube, let's say. This is the characteristic polynomial, and say the Cayley-Hamilton is saying that 1 plus, of course 1 doesn't make sense, that change to I plus 3s plus s squared plus s cubed, that was equal to 0. That's basically what we have. And so because of that, if you look at this characteristic polynomial, by the way, I have another video to talk about, a short video to talk about Cayley-Hamilton. I put the link there. You can, if you want to know more detail about it. I give a not complete proof, but just give an intuition why this hold. So for the where am I? Yes, for S here, let's say it's n by n, right? S is n by n. I have n nodes there, so, and therefore S is n by n, and the characteristic polynomial, apparently, if you look at the determinant of this guy, the degree of lambda cannot be more than n, right? So I have this degree of this polynomial here. I don't know what, yeah, maybe I put an error. Degree should be up to n, right? Has degree n. Have degree n. So that means that I from there from the characteristic polynomial is equal to 0, I can just reorder the things, and then I'll get some equality s to the power n is equal to a linear combination of lower orders there. So that means that if I have, it doesn't matter if I write a polynomial here to be longer than power n, or with degree larger than power n, but for whatever those values here, I can use this equation, substitute as n there, will get me back to a lower order equation. So in the sense no matter what I pick here, it's no difference from a polynomial representation up to the power Sn minus 1. So therefore the only coefficients that is this meaningful, that can uniquely represent a different filter, is only have n coefficient there. So basically if from n0 up to n minus 1. So therefore the degree of freedom of this representation here is only n. So it's pretty small actually. So if you think of the degree of this is only n, but if you think of the degree of freedom of the matrix, because the matrix itself is n by n, that definitely there's lots of matrix cannot be represented in this manner. So and as I said, for under some conditions, every filter, like every filter H that satisfy this shift invariant condition, I would be able to represent as this polynomial, but only for that particular condition is satisfied. Actually, one sufficient condition is simply S has to be have unique eigenvalues. So, but I am not going into detail for that one. I will leave it to another video. But here I just want to say that you can see there's a limitation here for this representation. Again, it doesn't matter. It looks like it's like this. I can extend this polynomial indefinitely, but the power of representation of this guy here is only you have degree n. So it's no different. Like no matter how many terms I add there, it's no different from like I have a polynomial up to like order n-1, something like that. So it's no different from this guy here. So therefore I only have degree n. N degree of freedom. Okay, so because of that, like researchers have been consider different cases, a different way to extend this. So one way is like instead I have like one scalar value here, maybe I can change it into a diagonal matrix. So for a diagonal matrix, it will be like local as well, because every diagonal matrix will be local, because if you remember like earlier, we say like we define a local filter is like it will only a node that to compute the future values of the current node will only take on the values or the signal from the current node or the neighboring node. So it can also take the current node here. So therefore, whenever you have a kind of a diagonal matrix, is always local. Then okay, like if I replace all this into a kind of diagonal matrix here, apparently I will have a much higher degree of freedom, and there will be some limitation as well. But I won't get into this one. Also, maybe in the future I may or may not go into this one, because for this paper here, he's not promoting this thing, he's promoting another thing. So this is an earlier work. This is a work actually, by the way, maybe I give the name, it's known as this node variant approach. At least this is like how the authors in the paper, and also in this paper, they call it like a node variant. It's node variant in the sense that like if you think of I only have a scalar value multiplied by this this shift operation, this operation here. So it's like that I have manipulate some values, I'm mixing of like p-fixed coefficients there, and I'm going to do weighted sum. Like I have this is like a final step to, you can think of like this is like I'm doing some manipulation of my using the shift operator to get like the computer values, and then I shifted I scale that as my, or like I weighted sum with other shift, other degree of shift to get the output there. But when I don't use a scalar value, but I use a diagonal vector here, diagonal matrix here, then essentially like I will have like for each of the node here, okay, think of maybe I write it more clearly. So I have like, for example, I will have maybe s to the k, right? S to k multiply the input like x here. So I have s to the k applied to this x. I do, this is some kind of manipulation. Afterward, like in the past, I would just multiply single values, a scalar value. Then it means that for each of the node, it will have the same. You can think of like not exactly the same, but the weight at least is the same. But here, if I have a diagonal matrix instead, so I will basically scale the input like from here, from this step here, by different values like for different node. So therefore like they call this a load variant approach. And in this paper, like if they just extend it further, they have this variant approach, in the sense that it's not just have this. Let me have some space here. Not just have this change this coefficient change to a diagonal matrix. It just relax it further. So relax it further into just a matrix here, an arbitrary matrix, but it's supposed to be a local filter. So in the sense I can change it to some phi here, let's say 5k, and my 5k should belong to the support of yeah. Actually, I think I have a different definition there. Yeah, that's indexable, but yeah, okay, I guess like this understandable. So something like that. Sorry, like it's a little bit different notation as before. But here what I want to say is like I will have this 5k can only be non-zero. Maybe let me write not using this support notation here. Maybe I just say like this 5k here. Maybe I write like k here, 5k. The ij element is non-zero if and only if like s plus I itself, like the ij element is non-zero, something like that. Actually, I don't need if and only if. I can have if. Like it's allowed that like even this is non-zero, this can be non-zero. It can be zero as well. So maybe I should say like only if. Okay, maybe I should just say like the opposite, like if this is zero, so that means that if this is zero, then this will be zero. That should be fine. That should be fine. So whenever like this zero, that means there's no edges there. Like then I have to force that the coefficient there has to be zero. So that would be like this 5k here maybe. So then I will have another this edge variant approach. So it's edge variant because if you think of that, like if you just doesn't, I mean if you allow the off diagonal term to be non-zero as well, the off diagonal term is essentially like mixing the edges. So it allows you like for each of the edge, like when the signal get into like each of the edges can be different. I will have in the sense like something like that way. So I will have like a filter something like 5k minus 1 sk minus 1 and so on and so forth, and plus 5 0. And by the way, like this is not the most general case. They call this constraint case, constraint edge variant approach. So and they can have a general approach, like just edge variant approach. They will instead like don't have this shift operator, or like you can think of like the shift operator can be different every time. So they basically have something like 5 0, 5 1, 5 2, and so on, product of that. Maybe like that. So what they propose is like 5 0 plus 5 1 plus 5 0, and then plus 5 2 5 1 5 0, and 5 3 5 2 5 1 5 0, something like that. They call this a edge variant approach. Let's see. I just make sure. I call them according to the paper. Yeah, this they call it edge variant. It's like this. Yeah. So So okay, now I guess what I'm going to do is I am trying to go more detailed just for this adjacency approach, like this adjacency approach, and also this constraint adjacency approach, and just follow what the author said. Kind of like derive some of the property of these approaches, and then describe the design paradigm for these approaches.